All right, almost 4 minutes have passed, so I think it's a good time to kick off. So welcome everyone. My name is Ivan Lazar Bundalo, and I'm a senior R&D engineer at CSTM, which is a Swiss Center for Electronics and Microtechnology. And it is my pleasure today to be your host on the first cFLOW webinar. So probably the first question, what is cFLOW? It probably makes sense to address that first. So cFLOW stands for coherent, ultra-fast, long-wave infrared communication. So that's a mouthful. So cFLOW is an EU project addressing long-wave infrared technologies with the goal of developing free space communications, but more broadly to further technologies addressing this part of the spectrum. So what's part of the spectrum? What's really special about this part of the spectrum? It probably makes sense to look at the graph of the electromagnetic spectrum and the attenuation of our Earth's atmosphere. So technology story is relatively simple. The bigger the attenuation, the less usable the part of the spectrum is. So what we have is on the left-hand side of the spectrum, we have all technologies. So the conventional radio, TV, and mobile networks. So they go down to some 1 millimeter long waves. This is where the first satellite and free space communication technologies were developed. So on the right side of the spectrum, we have the visible spectrum. The visible spectrum is mostly attenuated by the Earth's atmosphere. Now, around 1.5 micron is where majority of the presently telecommunication technologies are developed. So that's where the fiber optic low loss window is the place and where the majority of the lasers, detectors, switchers, and other technologies exist, which are making the backbone of the Earth's network. But with a bit longer wavelengths, over here, we are coming to the cFLOW project and the goal of the project, which is developing 8 to 14 micron wavelength. So that's the long wave infrared region. This region, as you can see, it has lower absorption than the region with the bigger wavelengths, and also some regions with smaller wavelengths. But the lack of technologies made it unreachable until very recently, when this has been enabled with the development of quantum cascade technologies, which are allowing to tap into this unused band. So the goals of the cFLOW project are developing the 8 to 14 micrometer spectrum to enable that for the free space communications and to allow for the unmatched speeds of the free space communication, so from 20 to 100 gigabits per second range, and to do all of that at room temperatures and in compact systems which are enabled by PIC technologies. So that was in short a bit now about the cFLOW project. You joined here because of the webinar. So we organized a series of webinars which are addressing these technologies, where we're going to have experts in the field talking about different struggles, different achievements, and the state of the art of the technology developed within the project and outside of the project. So in this, we're going to have these webinars every second Wednesday starting today. And without further ado, we have two speakers today. And now it is my pleasure to introduce on the left-hand side the first speaker, which is Carlo Sirtori. So Carlo Sirtori received his PhD in 1990 from University Milan. And the same year he joined Bell Labs. There he was one of the inventors of the quantum cascade laser. And then after that, he worked for Thales Research and Technology, so TRT, University Paris Diderot. And since 2018, he's a professor with École Normale Supérieure and holds the ENS Thales Chair of the Center of Quantum Devices. So Carlo, welcome. I would hand it over to you. Thank you for being with us. We are looking forward to the talk.
Thank you very much, Ivan. Hello, everyone. I'm going to share now the screen, and hope everybody can see it. Is that right?
Yeah, if you can just turn on the full screen mode, that would be better. Thank you.
Is it working?
That works.
Full screen, okay.
It seems to be, yeah.
Okay, good, excellent. So it's going to be a very simple presentation about the device that we're making, and just a little review of, let's say, the principle physics of let's say that are underlying actually these devices. And first of all, I mean, is this definition, which is important, is the unipolar optoelectronics, quantum optoelectronics. And the reason is because we are dealing with unipolar transitions, optical transitions. And it's actually, this is because I don't have the time, but to talk about it, but obviously we are very, very, let's say, very thankful to the grower of molecular beam epitaxy or all the other epitaxial technique that actually gave us the devices. And in fact, it's a quite complicated issue from this point of view, even though actually the technology of MBE is a very, very, a level of maturity where it's not a problem, is highly industrialized. But here you can see a nice TM picture where we see what we do fundamentally is our building block. So it's you have this sandwich fundamentally is in the very important part is the well here is the darkest part where we have a different material, but within the same crystalline structure. And the important thing is really that topologically we have exactly the same structure, but the chemistry is different. So here we have a material which was called barrier material and a material which is the well material. And fundamentally what matters is that the electronic affinity is different, and therefore electrons are trapped into these thin layers. As you can see, here is about, in this case, is 25 angstroms. So an electron are trapped here, and what matters also is that let's say, well, we'll see in a second. This is again, just to give you an idea, it's a three-dimensional problem. Even though, I mean, the problem is so nice that at the end, what we're going to do, we're going to really deal fundamentally, because the symmetry of this problem is that of the three-dimension, fundamentally this part is completely forgotten, the part that actually have free electrons, and we design our device and our structure by taking care only on the part which is quantified, because the length of the quantum well is so thin, as I said before, I mean, a few tens of angstroms, that therefore the energy and all the properties of quantum mechanics becomes actually possible, given also the fact that the mass of the electrons in the semiconductor is very light. And therefore we have quantization, we have the formation of these wells. Now, so that's really why we're talking about unipolar optoelectronics. Again, let me get here, is because you see, whatever it occurs only in the conduction band. And you see there's no electron hole recombinations. Everything is only electrons in a quantum well. So it means that actually we have doped semiconductors where the electrons in the conduction band are confined and in very thin layers that forms quantum well. Okay, so this is again the same thing, just to remind that the nice thing is that this part here, let's say the height of the quantum well, or the depth of the quantum well, is about half an electron volt. So, which is several times the kinetic energy, the thermal energy that electrons can have, and therefore what the electrons are, let's say, into the well, are trapped. And there's no possibility with just thermal energy to kick them out. So they are stably into the well. And the nice thing is also that when we do transitions, we really, even though we have bands of electrons, we have we experience an absorption which looks really like an atomic transition. So really the same shape that we would get if we had just two levels. Now, it is important to say that those are not electronic quantum levels per band. And this is, I mean, for today, it is important just because it means that we can accommodate many electrons and not just two classical, up and down spin. It is, in fact, it is a big advantage is that therefore on these subbands we can put billions of electrons. and therefore be much more efficient in whatever gain or absorption. This is also the extremely important part, is the fact that we have, let's say, not just quantum well, but is the possibility to couple them through tunneling barriers, as can be seen here or there. And the possibility are very, very general. So, we can do symmetric structure or break all the symmetries, as you see on the right-hand side. And therefore, coupled and having coherent wave functions across the several interface between wells and barriers. The whole, let's say, theory of this is, very well known. And so the possibility of being predictable, so we know exactly what we have to do or design the wavelength for the laser of the detector is also, quite assured by this theory. Now, as of today, we have 4 main devices. 2 are detectors, are on the top here. This is the first one, the quantum well infrared photodetectors, and then we have quantum cascade detectors. And those are really devices where an electron, actually the energy of a photon, can be converted into a photocurrent. Quantum cascade laser is probably the most famous, and even though it's not the first one, actually is the one that had a better, higher success. And today actually is really commercially available, and that's one of the things that also we are exploiting in our labs or even in our projects. And the last thing is that we made it recently is the start modulators. Which is, let's say, a possibility, again, a device that allows us to have to modulate for the moment in amplitude, but we are also exploring the possibility of having phase modulation. For the rest of the talk, I'm going to tell a few words more about these 2 devices, which are the most recent and the one that actually are mostly involved in the project cFLOW. Before getting to the device, I think that the most important why these devices are very, very fast. So they have an intrinsically ultra fast relaxation lifetime. So it means that electrons were on the excited state, they stay on the excited states only in the order 1 picosecond, which is excellent because it means that actually they never saturate fundamentally. And also they refurbish immediately, whenever you send electrons up in the, for instance, in a modulator, they stay very little and they come back immediately on the ground state. And that allows you actually therefore to modulate in extremely fast bandwidth. This is true for absorption, is as well true for the gain, and therefore lasers also can be modulated very fast and directly by acting on the current. Also, which is quite important, is that the energy of when the relaxation time, let's say, is dominated not by photoluminescence, but rather by a non-radiative recombination. So in fact, actually, this device has almost zero luminescence. Now, quantum cascade detector is actually quite interesting because it is, you see, a photovoltaic detector because wells and barriers, this is actually a very simplified design, being combined in a way that when photons arrive, it promotes an electrons from the ground to the excited states, and then the electron can tunnel out. And this is the important part. Within the structure, we have designed a pseudoelectric field which sweeps away the electrons very fastly and bring them in the next adjacent well on the right side here. So this is, a very fast detector, even though it's a photovoltaic. So it has an extremely extensive gigahertz of response, even though actually no bias, no electric field is applied on the structure. This is quite unique in its way. Now, just to show you the reality is as usual more complex. Well, exactly the same thing that I described is actually obtained by a series of quantum wells and barriers coupled in a different way. The other important device, I would say, is the modulator. And again, I mean, in this case is, we call it asymmetric coupled quantum wells. The third level here actually can be completely forgotten. What matters is here, the level 1 and level 2, doping as usual, you know, the structure. And the laser that we are using is very close to this transition 1 to 2. So the energy of the photon here are close to the difference between 2 and 1. Now, in this case, actually, what's going on is that this device undergoes a Stark effect. And it is actually the little cartoon here to show. And so you see, whenever we apply a bias, and then you see we are applying a bias, we are lifting actually the structure in this way. You see that these two transition, actually the separation, the transition gets bigger and bigger. And this is what's going on to the absorption. So the absorption line, as a function of the bias which is applied, moves and hits the laser line, and therefore there's absorption. It means that here there's absorption, here not. And so again, I mean, now this is, you know, in a loop. So we keep on seeing the same thing. But this is exactly what's going on when we do absorption. So it means actually we're modulating, we're applying a bias, as you can see on the left side, and the laser line is hit by the absorption regularly, and therefore his intensity is modulated. What we have done actually is bring together, but I just mentioned a few words because this is really for the next talk, and the laser, modulator, and detector, and this is the detector and the modulator are really the one that I just described. And you know, we here is again a simple the schema of the system. And you can see those, the blue are the input and the reddish here is the output, and those are bits. And you see we introduce a number of bits and we can read them out from the detector. And we went up to a few tens of gigahertz, and those are really the first one that really worked in my group, Hamza Daly and Tomar Bonazzi, that made the first modulation. One thing which is important also, and that's why we were going and we're trying to implement, is work on metamaterials in order to make this device more efficient, is to break the surface into very small bits and take advantage of antenna, because we are in a frequency range where antenna actually can be used without too much losses, and enhance the light matter interaction in a way and reduce fundamentally the the size of the device. In a word, what we do, this is a few examples of a lot of the work that we are doing at the moment, where you see the typical features in the order of 1 micron. But what really matters is what you see here. It means that given the fact that on the top of each element that we're using, we put gold, we have an antenna effect. And so electrons from far away are funneled into this structure, as is showed here in the picture, and allows us, therefore, to go in this way. So you see, there's no photon that will hit in the middle because it will be catched by the antenna. And so the main message, which is excellent for modulation, because we reduce the size and therefore the capacitor, is that we separate completely the optical area, which stays as a large area due to the antenna effect, from the electrical area, where actually we have to count just the sum of the little bits that we fabricate. And in this way, actually, we are really hoping, actually, we know already that we can gain a lot in frequency, because we can get rid of a good part of our parasitic capacitors. That's the end of the talk. So it's just re-mentioning what I just said. Unipolar, because no holes. Ensemble of devices all operating at room temperature, which is very important. They are very, very fast intrinsically, but then, you know, you have to deal with the RF. And also this, I would say, is a very important issue. We are dealing with devices where conceptually are new, but they are embedded into the technology which is already well known, which is the semiconductor technology, fundamentally of telecom 1.55. Moreover, actually, you know, is a kind of platform that could be maybe hybridized in future with also 2D materials. Thank you very much for your attention, and I hope I stayed within the time.
Thank you, Carlo. That was very interesting. We do have a few questions over here, so I will jump straight to them. So the first one is, you are developing an entire new optoelectronics in thermal frequency spectral range from 8 micron to 12 micron. Are there any possibilities to have fibers in this wavelength range, and imagine to conceive and realize communication system as we have today at 1550, so at 1.55 microns?
It's an interesting question, because we do, there is a fibers, particularly at 9, between 9 and 10, they start to be quite interesting, and there would be a really a tremendous help for the technology to maybe not to go across the ocean like we do at 1.55, but at least maybe, you know, to deal on hundreds meters, maybe 1 kilometers. Still, the technology, I'm afraid, is quite young, and there's some work to do. But I think actually it's really on us also to be a bit more, let's say, upgoing towards this and try to exploit more what is already existing. Mere Sense, by the way, also is already using fibers. I don't know to which extent, but I know actually they do have it.
Very good, thank you. So we have another question. What is the possibility of integrating the different devices that you have showed us?
Well, this is really the issue of one of the important issue of cFLOW, and so I would say that this is the way to go. So we are on the right track with our project, and it's what we have done is really demonstrated the concept and showing that actually they're very, very fast. It is, one of the, I would say, really to make this real, to make this technology really possible to be transferred is the integration. And so I think that really we can take advantage fully from the fact that we are dealing with semiconductor technology, which is very mature, already existing, and therefore, actually, I think that it would definitely possible to do it.
Very good, thank you. We have another question, but you somehow answered that already, so I'm going to go for the last question that I have available here, which is, how large is the modulation depth achievable with the Stark modulator?
It is now we made the full, let's say, a good quantum model of this, and in fact it's very, very high. We can go up to about 250 gigahertz. This is really the physical systems, and which is also we understood that the modulation is a modulator where the physical principles are not on the lifetime of the electrons, but on the coherence time of the electron. Those are details, but to say that it's really is the shortest probably process that we have when we have an optical transition between two electronic states. So that's really encouraging. And then so 250 gigahertz is possible. The difficulties is then to make to make the packaging around these devices that allows us to get up to such a high frequency.
Very good. Thank you, Carlo. So it seems like we do not have further questions for now. What I can do is also, if we are on time, we can also take some questions at the end. But then for now, I would like to thank you, Carlo. Very interesting. And we will go on to the second speaker for today, and that's Xiaodan. So just a second here to open.
Thank you very much to all of you.
Thank you. Okay, so I lost my screen over here for a second. Yeah, so Xiaodan Pang is a senior researcher at the Applied Physics Department at KTH, so Swedish Royal Institute of Technology. His research focuses on high-speed data transmission technologies with free space optics. That goes with millimeter waves, terahertz, RF photonics, and fiber optics. He's the author of over 200 publications in scientific journals and conferences and has given over 20 invited talks at international conferences. So Xiaodan, we are happy to have you here. The floor is yours.
Thank you. Thank you very much. Let me go ahead and share the screen. So can everyone see my screen in full screen mode?
Yes, we can see it.
Okay. All right. So thank you again, Ivan, for the very kind introduction. And it is my great pleasure today to contribute to this webinar and talk about our recent research efforts in the field of free space communications at room temperature enabled by quantum cascade lasers and detectors. So Professor Sirtori just described a lot of details focusing on the components device level. So my talk will focus on the communication system level. And I will start by motivating our research from the point of view of applications. And then I will guide you through our recent efforts in terms of experimental demonstrations on the system level transmissions. And we have been improving progressively the data rate supported by the quantum cascade lasers in the mid-wave and long-wave infrared. And I will show you what we have been doing. And in the end, I'll summarize and conclude. So nowadays, we know that we are entering a digital era, and a lot of applications has been made possible, including the webinar that we're having now. So into the next generation, because now the 5th generation of the mobile networks is being deployed, and into the next generation that is anticipated to be 1 decade from now, we are actually talking about almost 2 or 3 orders of magnitude higher data rate demand because of the envisioned application of virtual reality, for instance, the metaverse that everyone is talking about these days. And in order to do that, we have a great pressure imposed onto our ICT infrastructure, including both optical fiber communications and wireless communications that has been running with radio technologies. And great challenge ahead, but also great opportunities. So in order to unlock such a limitation, according to the Shannon's theorem, the most straightforward way to have a broader bandwidth. And this creates new opportunities for us to seek new spectrum range where we can run our communication systems. So ultimately, we hope that we could reach a unified electromagnetic resource pool, regardless whether we're coming the spectrum coming from the optic side or the radio side or somewhere in the middle. So if we could manage to synthesize all these physical layer technologies that we have accumulated from both optical communications and wireless communications with the resources that we have across the electromagnetic spectrum from the radio to the optics, including the microwave, millimeter wave, terahertz, infrared, visible light, everything, and also the media that we have, optical fibers, free space, or somewhere in the middle with energy. So in the end, we hope the end user's demand can be realized instantaneously, regardless whether the technology of the resources coming from the optics side or the radio side. So in order to achieve this, we need equal technology readiness level across the spectrum, which we are not there yet. And the most or the least exploited frequency range is right in the middle of the spectrum we're talking about. And on the in the figure from the left-hand side, we show the atmospheric attenuation across the electromagnetic spectrum, including both optics and radio. So where we have the mid-infrared in the middle of the spectrum, there are 2 transparent atmospheric windows. namely the mid-wave infrared from 3 to 5 micron and the long-wave infrared from 8 to 12 micron. If we compare these two windows with the right-hand side of the spectrum, where we have the millimeter wave and terahertz, and which has been discussed and started intensively these days for the next generation wireless communications. If we compare these two, then we know that we can directly observe that this mid-wave infrared and long-wave infrared suffers almost 2 orders of magnitude lower attenuation compared with millimeter wave or terahertz. And also they are license-free, so we can run basically parallel channels in this spectral windows with wavelength division multiplexing that we have been doing in fiber optics. And also they have much wider spectrum or bandwidth available for communication purposes. So when we're talking about candidates or solutions for next generation wireless communication, I mean, this mid-wave infrared window should be considered. And if we compare these two windows with the other side of the spectrum, where we have the shortwave infrared or 1.5 micron telecom band, these two windows suffers or they have much higher robustness and lower sensitivity to atmospheric perturbations, including the scattering from the aerosols or the turbulence-induced scintillation effect or beam wandering effects, things like that. Also, this mid-infrared windows has a better eye safety threshold. So there are a lot of good properties lying within these windows. However, they are currently underexploited. And the curve, the figure on the right-hand side shows a comparison between the 1.5 micron and 9 micron in terms of the attenuation against the visibility. We do see that across all the visibility range, the 9 micron shows a better or a lower attenuation. So which means that a clearer channel can be opened up with mid-infrared, where the 1.5 micron might have been blocked. So actually, the optical communication community has been looking into mid-infrared free space optical communications from some time ago. And one of the first demonstration were based on wavelength conversion, where basically we can reuse the telecom transceivers, where we transmit and receive the signal in the telecom band. However, we can do a wavelength conversion to convert wavelength to the mid-infrared, to up convert and down convert the wavelength before and after the free space link. And back in 2008, this work was reported at Optical Fiber Communication Conference, OFC, where a 2.5 gigabits per second QPSK was transmitted through a 3.8 micron free space link in real time. And extending this concept further, 2 years ago, we saw that a demonstration of up to 10 gigabits per second QPSK transmission has been achieved. And also they made a quite compact or relatively compact module compared with 10 years ago. However, they do have amplifiers and this difference frequency generator crystal units here. So they're still bulky in size. Further extending this wavelength conversion concept. Last year at OFC, colleagues from the University of Southern California has reported up to 300 gigabits per second aggregated transmission by using multi-dimensional multiplexing, including both wavelength and mode division multiplexing in the range of 3.4 micron. So a very impressive results. So to conclude, by using the wavelength conversion scheme, we can keep up the speed or the development pace of fiber optic communications with very short gap lag behind. However, I still would like to motivate the use of semiconductor-based mid-infrared transceivers. So I list the pros and cons between these two concepts here in this slide. So for the wavelength conversion scheme, it can support very high transmission rates, and they are compatible with the fiber optical systems. Basically, they can reuse the transceivers so that they can be developed in very short term for high-end and specific applications already today. However, on the downside, it's very hard to use such a scheme to support long-wave infrared and terahertz range, because most, if not all, the demonstrations with this game or demonstrated below 4 micron wavelength. And wavelength conversion based on nonlinear process, they are not really famous for their energy efficiency, and also according to what we observed, such a nonlinear process or such a nonlinear module is very, very difficult to miniaturize into the chip level. So on the other hand, semiconductor-based transceivers, in our case, the quantum cascade laser, quantum cascade detectors, they have the potential to cover a very large spectrum range from the mid-wave infrared down to the terahertz. And they can be made very small in size so that it's easy to integrate. And because they are based on semiconductor technologies, they can be made very energy efficient with quite high up-to power. And in the long term, once it's mature, we can expect large volume development and wide deployment of such transceivers. However, apparently now the maturity is low because there are no low-hanging fruits here. We cannot really reuse any of the fiber optic components that has been developed for the telecom band in the 1.5 micron. We really need to reinvent and redevelop a lot of new things at this area. And there are also fundamental challenges to overcome. For instance, high temperature operation is challenging. It's more challenging than the 1.5 micron. And it's also difficult to support high bit rate because the maturity of all the active and passive components are still low. So we really need to start from the scratch to build up system in order to show that the high data rate can be possible. So this is exactly what we have been doing over the years. So back in 2017, this was actually our first attempt to transmit over such a directly modulated QCL based link at 4.65 micron in collaboration with Mearsense and RISE. We basically have reused a lot of expertise and technologies that we have accumulated and gained over the research in the fiber optical communications. So for instance, we performed a large, to a large extent, the pre-emphasize in the frequency domain. So despite of the low frequency, the very low 3 dB bandwidth around 300 megahertz and 6 dB bandwidth around 400 megahertz, we managed to squeeze in up to 3 gigabits per second of keying signal by performing really heavy pre-emphasis. So basically, we suppress the low frequency and enhance the high frequency components of the spectrum by a large extent, so that we have equalized signal spectrum after the transmission. And also one more thing is that due to a imperfect engineering at the time, we didn't really have a collimator at the output of this QCL. So the transmission distance was limited to 5 centimeters at the time. However, we do see a very good properties of the system because we managed to see very clear eye diagrams for both, for all 3 modulation formats that we have tested, including this on-off-keying, NRZ off-keying, PAM4 and PAM8. And all of the 3 modulation formats has achieved up to 3 gigabits per second at the time. And we do see a very good linearity across the different modulation formats. So 3 gigabit of off-keying shows a great performance or characteristics of the noise performance, particularly at high frequency range of the spectrum. And the low baud rate PAM8 modulation shows a very good linearity in terms of both modulation and detection. And at that time, also tested the system or the transmission stability, and all 3 modulation formats the performance has been quite stable over almost half an hour. So, well, based on this work, we do see that PAM4 seems like very good, the sweet spot between the 3 modulation formats, and so we basically extend this modulation formats to support to explore the highest achievable bitrate with the same system. Basically, we have the same setup, but this time we focus on PAM4 and try to increase the bitrate against the hard decision fact threshold, and compare with another modulation format, which is the digital multi-tone modulation format, where we have been using subcarriers. I will show you in the next slide. So both modulation formats, we achieved up to 4 gigabits per second this time. And again, very good linearity has been observed. Also with the DMT modulation formats, where we have different subcarriers modulated with different level of modulation, so that we can maximize the efficiency, the spectral efficiency across this colored SNR. However, we don't really see much improvement in terms of bitrate because the very good noise characteristic and of the transceiver that has been used, so that even though we could fit in a better modulation formats in some of the subcarriers, we don't really see much improvement. And also the more number of subcarriers we use, the more peak to average power ratio that will suffer in the modulation, so that actually there is a trade-off there, preventing us to achieve much higher speed than the PAM4. So that's why in later demonstrations we focus on the PAM modulation, because it's much easier to implement and it's straightforward. So well, it took us 3 more years to install this beam collimator. However, by doing that, we managed to further increase the transmission distance and also enhance the receiver side signal noise ratio. And in this work, we managed to increase 50% on the achievable bit rate, so 6 gigabits per second with the same transmitter and receiver. And this time, we again tested 3 modulation formats and try to explore the highest achievable bit rates against these 2 commonly used forward error correction thresholds in the telecom system. And these are the results. So at the KP FAC, or 2.2 E-4 BR, we managed to achieve up to 4 gigabits per second NRZ, 5 gigabits per second PAM4, and 6 gigabits per second PAM8. And if we use a higher threshold, 3.8 E-3, hard decision fact threshold, which has slightly higher latency to code and decode, we could reach 1 gigabit higher data rate for or 1.5 gigabits per higher data rate for PAM8. So up to 6 gigabits per second transmissions are achieved in this setup. So it's worth mentioning that we have never used any nonlinear equalizers in this setup, because we do see the linearity was not really a problem. So this work was reported last year at ECOC. So lately, we team up with Professor Sirtori and Professor Vassanelli's group at ENS, and we join our force and move to a different wavelength, which is this long wave infrared 9.6 micron. And we focused on, again, on the direct modulated QCL. And this time we managed to use a passive quantum cascade detector that is also developed at ENS. At the receiver side, we managed to achieve up to 11 gigabits per second. So this is the setup. We have the QCL was a 3 millimeter long ridge laser, and we operated at 0 degree. And then we use a 2-stage focusing collimation focusing length to really reduce the spotlight at the receiver side to maximize the detection efficiency of the QCD, because it's really sensitive to the alignment and to the focusing. So one more thing to show is that the peak responsivity of the QCD was actually around 8.75 micron. So because our wavelength at 9.6 micron is a little bit shifted from the peak responsivity, so the detection efficiency was not really at the maximum, but at around 45%. So we do see there are certain room for further improvement. And we perform end-to-end system calibration. So this is a very common practice that we have been doing in telecom, in fiber optic telecom systems. So, and we use both pre and post equalizations to flatten the channel response to maximize the signal quality at the receiver. These are the results. So this time we benchmark against the 6.25% hard decision factor, and we have achieved up to 8 gigabits per second NRZ below the hard decision factor limit, and 5.5 gigabaud PAM4 corresponding to 11 gigabits per second below this factor limit, and further increase the bit rate by 500 megabits per second is no longer possible. We do see that no matter with how complicated equalization, we are not able to bring this curve below the factor limit. And we sweep this BER curve, or we sweep the power by changing the driving current. This is normally we don't do in fiber optics. However, because we don't really have attenuator for us to play with, we have to do this in this way. But we do observe interesting trade-offs by sweeping the laser current. Well, just across the threshold or above the threshold, we do see there is certain compression the lower side of the amplitude levels, because once the modulation index is high, we're really hitting the threshold. And we find the sweet spot when we increase the laser driving current up to 630, 640 milliamps, and where we have a good compromise or balance between the noise and the linearity. Further increase the current, we do see compression started to be observed from the upper amplitude levels, and in the end, once we reach the roll-off point or saturation point, we have a very bad performance. Even though at this point the signal to noise ratio of the receiver is really maximized, but the signal quality has been distorted severely. And this work was reported at OFC post-deadline session last month. So here's a summary of what has been going on in the mid-infrared free space optical communication. Not really mid-infrared, from mid-infrared down to the terahertz free space communication, but with direct modulated QCLs. So long story short, during the past 20 years, a lot of work, well, not that many works has been done, but in the beginning, most of the works are focused on low temperature operation, and until recently, after 2010, more and more work started to be operated at room temperature, or at least a higher temperature. And we have contributed in this process, starting from 2017 until today. We have progressively improved on the achievable data rate, and now we have achieved 11 gigabits per second. And we hope this is not really the end. We will continue working on this by synthesizing all the expertise we have accumulated from different areas, including optical fiber communications. So to summarize, we are still continuously working on direct modulated QCL-based free space communications in the mid-wave and long-wave infrared, and we're trying to progressively improve the higher and higher data rates. And we have accumulated a lot of expertise and experience from the fiber optical communication community. One thing is the use of advanced modulation formats. The other thing is to use novel pre and post equalization techniques. And this is only the beginning of our effort towards a envisioned, fully connected mid-infrared free space network. Hopefully one day we could have a mid-infrared free space network running in parallel along with the fiber optic networks and the RF-based wireless networks that has been supporting our society nowadays. And as I have said during the post-analyze session at OFC last month, there are a lot of works to be done, and it won't be up to us to decide whether or when this will be used, but it will be up to us to decide to make sure that they are ready by the time it's needed. So we look forward to more collaborations, and we also look more forward to more computations. So with that, I would like to thank you all, and let's join forces to make it happen. Thank you very much.
Thank you very much, Xiaodan. Very interesting talk. So we have just a few minutes left, so I have a limited amount of questions that I can take. One of them you apparently answered in the summary slide, well, the slide just before this, so I'm going to skip that one.
All right.
There's one that says, what optical links, so wavelength and modulation format, you find the most promising for the future of free space communications, and which one you find the biggest competitor then to okay, I think that was misplaced. Okay, so maybe just the first part. What optical links or wavelength modulation format you find the most promising for the future of free space communication?
To me, from my personal point of view, I think if we don't consider the maturity or technology readiness level differences between all the segments of the spectrum, I do believe the long wave infrared has a great potential to be developed into a real system that can support mid-infrared free space communications in parallel with the wireless communication and the fiber optic communication, because they have quite unique properties that can be used for communication that is really difficult to be achieved with the shortwave infrared and with the millimeter wave terahertz. So that's my personal point of view. But of course, challenges are there. As I said, there are a lot of challenges because everything was need to be redeveloped from scratch, and there is no accumulated critical mass yet, and there are no development momentum from the industry. So it's up to us to push it.
All right, thank you. Then there's another one. How to further increase the data rate towards and beyond 100 gigabit per second?
Yeah, thank you. This is the question I've been thinking about almost every day. And well, we have from the system level, we basically could use whatever that we have in our hands that has been accumulated from both the fiber optic communications and the RF communications. But in the end, we're limited by the channel limit. So basically the signal noise ratio and bandwidth. So we count on the fundamental breakthroughs in the device level. So according to Professor Sirtori just said, up to 250 gigahertz can be realized with this unipolar quantum cascade devices. We really look forward to make use of this bandwidth. And if we really could have that bandwidth in our hands with satisfactory signal noise ratio, noise performance, it shouldn't be a problem for us to build up a system running at high bit rate up to even higher than 100 gigabits per second, even with much longer distance. Yeah.
Very good. Thank you very much, Xiaodan. With this, then I would like to conclude the talk for today, and I would just like to share quickly a slide. So I hope that you can see that. So you can find more information about our project and also webinars on our webpage, so cFLOW-project.eu. And I hope to see you again next time in 2 weeks' time, where Salvatore Pes from the 3.5 Labs is going to present optical communications in the long wave infrared window, and Borislav Hinkel from TU Wien will present mid-infrared plasmonic waveguides. So with this, I would like to conclude. Thank you all for your attention, and have a great rest of the day.